Hi everyone, we introduced ProtoCon for semi-supervised image classification. ProtoCon addresses label scarce regimes when only a very small portion of the data is labeled. First, for each unlabeled image, we obtain a pseudo-label which is the model's softmax probability. However, this is usually prone to overconfidence, which increases the chances of a confirmation bias. Hence, we jointly train a prototypical representation space where our images are all projected. Subsequently, we obtain a secondary pseudo-label based on the image's nearest neighbor in that space. Finally, we combine the two to obtain our final refined pseudo-label. This is used to train the network via a consistency regularization objective. ProtoCon employs online constraint clustering to identify the neighbors without needing to store image embeddings. This leads to a 16x reduction in memory requirements while achieving state-of-the-art performance. Now let's break this down in more details. To begin, we first review fixed bench, which is a seminal baseline forming the basis of recent state-of-the-art methods. This recent family of methods employs the idea of pseudo-labeling and consistency regularization to benefit from the unlabeled data. For each unlabeled image, a weakly augmented version is used to guess a one-hot pseudo-label. Subsequently, the model is made to predict the same pseudo-label for a strongly augmented version of the image. A confidence threshold is employed to ensure that only samples with high confidence are retained for pseudo-labeling. While this approach works reasonably well in moderate data regimes, it tends to fail in label-scarce settings when we only have a handful of samples per class. This is primarily due to confirmation bias, where the model reiterates its strong predictions by further training on them as ground truth. Our key finding is that it's possible to refine the pseudo-label by employing multiple learning objectives. To illustrate, imagine we train multiple projector networks sharing a common backbone, where each of those networks is required to implement a different learning objective. For example, the first predicts one of n classes, while the second predicts the class or pseudo-class prototype of a given sample, and the third is tasked to match strong and weak augmentation. What happens is that each representation space learns a different mapping or view of our images. Accordingly, we find that images cluster differently in those different projection spaces. For instance, in the head trained to predict prototypes, prototypical images of classes are clustered together, while for the head matching augmentations, images with similar parts and patterns cluster together. Hence, we can obtain not one, but multiple pseudo-labels for each of our unlabeled samples in each of those representation spaces. Simply, a sample can be represented as the average of its n nearest neighbor's pseudo-label. Now, once we have all the different pseudo-labels, we combine them into a single final pseudo-label, which we use to train the network. To implement this idea, however, one major challenge is how to identify the n nearest neighbors of each sample in each iteration as we train the network. One naive way to do it is to save the projections of all the images in all the different spaces and perform an offline clustering step after each training iteration to identify neighbors. This solution, however, is slow and extremely memory intensive and hence cannot scale for large datasets. Our solution was to address this problem using online constrained k-means clustering. By adopting a mini-batch version of k-means, we can perform the cluster online, where the k-means centroids are updated after each training iteration. Additionally, by constraining the cluster sizes to n samples each, we ensure that any given image has n samples in its cluster. Now it becomes a matter of keeping track of the cluster assignment of each image as we train the network to identify the nearest neighbors on the fly without needing to store embeddings or perform offline clustering. Combining these ingredients gave us ProtoCon. ProtoCon combines different losses to jointly learn 1. A prototypical projection space defined by our projector H. 2. It learns to match strong and weak augmentation via our consistency loss. And 3. It learns our cross-entropy classifier based on the pseudo-label obtained via our refinement strategy. All this is done online by employing our online clustering approach. ProtoCon achieves 16x reduction in memory requirement and set state-of-the-art in semi-supervised image classification in the label scarce regime, which we define as 2 to 10 images per class. We evaluate ProtoCon across different SSL benchmarks and in different visual domains such as clip art and sketch. All our experiments focus on the scarce regime, where we have access to less than or equal 10 labeled images per class. In all settings, ProtoCon achieves state-of-the-art or near state-of-the-art performance. Additionally, we investigate how the diversity of objectives help with the refinement process. In this graph, we display in orange the original softmax pseudo-label, in blue the prototypical pseudo-label, and in green the refined pseudo-label. We can see first that the disagreement between the two pseudo-labels, which is the dashed black line, decreases as training progresses. And we also see that the refined pseudo-label, which is represented by the green curve, is always more accurate than the individual ones, which demonstrates the effectiveness of the refinement procedures. In our qualitative experiments, we investigate when each of the two pseudo-labels are more accurate. The images on the left depicts the instances where the softmax pseudo-label is on average more accurate than the prototypical pseudo-label. Conversely, the images on the right are where the prototypical pseudo-label is more accurate. We see that on the left, the images exhibit distinctive but less prototypical features, such as the truck wheels and the bird beaks, while the ones on the right are more prototypical in nature. Finally, we find that with the consistency regularization loss we introduce, ProtoCon exhibits faster conversions compared to the state-of-the-art. Thank you for listening. If you'd like to know more, please check out our paper and our code on GitHub.